this opportunity to discuss the current research what we are doing. So as you can see from the title, today we will discuss about the green ammonia synthesis. Firstly, I want to let you know that basically I am electrochemist, so I choose problem based on electrochemistry and energy perspective. So we are working on electrochemical ammonia synthesis, metal layer battery or fuel cell, water electrolysis and supercapacitor battery. So today only I will focus on this topic, electrochemical ammonia synthesis. So as you know, this ammonia been developed long ago as a fertilizer first. So India is consuming ammonia as a urea. So 50 million tons of ammonia we will be needing by 2050. So not only that, so 60% of total fertilizer we are using based on ammonia. But the problem is that ammonia, whatever we are generating, is not a green way. So we are trying to find out some process which we can synthesize ammonia by some green approach. So recently, Niti Aayog India also have shown that by 2050 we have to produce ammonia and by some green approach. So based on that, our motivation came that whether we can contribute something by electrochemical way for the synthesis of ammonia by the reduction of nitrogen. So the question will arise that can ammonia stop the whole addiction of fossil fuel or not? So the answer you will get to know by the end of this talk. So here you can see this process of synthesis ammonia is developed at the 1909, and this first industrial ammonia was synthesized at 1913. That means 110 years ago the process was developed, and till now we are using the same process by this Haber-Bosch process. So there is a quote by world largest ammonia producer company, Tony Will. So according to him, we are till now using the nitrogen part of ammonia. So now the time has come to market on this hydrogen part of ammonia. That means ammonia not only using as a fertilizer, we can also use it for energy storage. So there are some color codes of ammonia. So green or brown ammonia, blue ammonia and turquoise ammonia. So the electrochemical ammonia is found in this region, which we call as green ammonia. So now the question is, you know, this hydrogen we consider as a green fuel. So all of a sudden, why you are thinking about ammonia? So the answer is here in these two things. If you see this chart, if you compare liquid hydrogen and liquid ammonia, so here is this the temperature means storing both are in liquid form, but the storage temperature for liquid hydrogen is minus 253 degrees centigrade. That means you need cryogenic temperature. Whereas for ammonia, you need only minus 33 degrees centigrade. So this is the biggest advantage whether ammonia can replace liquid hydrogen or not. So another advantage is energy density. So if you compare their energy density, for liquid hydrogen it is 8.6 millijoule per liter, whereas for liquid ammonia 12.9 millijoule per liter. That means for the if you want to store equivalent energy content, ammonia needs less space. So because of this main two reason, ammonia can replace hydrogen if you can synthesis, if you can solve the other problems. So what are the other problems? So the main problem is we want to synthesize ammonia from nitrogen, which is an inert gas, all of you know. So if you compare their bond dissociation energy with their isoelectronic compound like carbon monoxide and acetylene, so although the bond dissociation energy is less than other two compound, but if you see their first bond dissociation energy, that is very high. For nitrogen it is 410 kilojoule per mole, whereas this is very less than this nitrogen. So this is the challenge, whether you can activate nitrogen on the catalyst surface or not. So you need some catalyst to activate nitrogen and then followed by protonation. So not only this bond dissociation energy, if you see this other parameter like homo-dumo gap, ionization potential, proton affinity, all are goes against this, means it is very difficult to break nitrogen-nitrogen triple bond and produce ammonia. So electrochemically also there are some challenges. First I will show you the electrolyzer, how we synthesize ammonia electrochemically. So this is the design of electrolyzer, where we have cathode and anode separated by a membrane. This is proton exchange membrane. So as it is reduction of nitrogen, that means our catalyst will be on the cathode surface. So cathode reduction will happen, And at anodes, so water electrolysis, because we are producing this ammonia in aqueous electrolyte. That means water will dissociate as anode, and this proton will move through this membrane and go to the cathode, and there we can reduce nitrogen in presence of this H plus and produce ammonia. So we have to pass nitrogen gas, and ammonia will be in the solution. So what are the challenges electrochemically? So these are the challenges. The first challenge is nitrogen solubility. As all of you know, nitrogen solubility in aqueous electrolyte is very, very less. So I mean, in this way we have to work out, or we can take other electrolyte, organic or ionic liquid, but there are also some other challenges. So our focus is on the solubilized nitrogen more in aqueous medium. So second challenge is sluggish kinetics of this counter electrode reaction, that means oxygen evolution reaction. Third challenge is this competitive reaction which occurs at the cathode, which is hydrogen evolution reaction. Because we are dissociating water, that means oxygen evolution reaction and hydrogen evolution both will occur. So there will be always competition of nitrogen reduction reaction to the hydrogen evolution reaction. And another challenge is the reduction of ammonia. Why this is challenge? Because you are reducing nitrogen to produce ammonia, but there could be some other source of nitrogen, like nitrogen can come from catalyst, nitrogen can come from electrolyte. So whether this nitrogen is itself reduced to produce ammonia, or your catalyst nitrogen or other nitrogens interfering, that is very difficult to get. So if you can overcome these challenges, then one day we can succeed to produce ammonia. So I'll go one by one how to address these challenges. So these are the descriptor how you will determine your ammonia is formed or not. So one is overpotential rate, Faradic efficiency, and production rate. So there is a chart, you can see this ammonia yield versus Faradic efficiency. So these red dots shows the literature report. So we are in this region, but actually we have to go to this green zone if you can produce ammonia or thinking to produce ammonia industrially. That means your Faradic efficiency should be more than 50%, and your yield rate should be more than 6,000 microgram per hour per centimeter square. If you can go in this region, so we can industrially produce ammonia through this electrochemical process. So and there are three detection method to detect whether ammonia is formed or not. We can you know this method from school level books also, because Nessler reagent method, indifferent blue method, and salicylate method. So because you know this ammonia is colorless compound, so we have to produce some colored compound so that by UV visual spectra you can detect ammonia. So these are nothing but to convert ammonia to some colored compound. So mostly we prefer this method, indifferent blue method. And literature also people are doing indifferent blue method or salicylate method to detect ammonia. But there, when we started this work, we faced that there are also a lot of discrepancies in the literature. What pH range we should adopt, what we should incubate it in dark or light. So several challenges we faced because it is a new field. I mean, only 4 or 5 years people are working on. So we have seen that in the indifferent blue method, although people are reporting, there are a lot of discrepancies. What are the discrepancies we find out? Before telling that, I will tell you how this color compound is generating by these three steps. First, ammonia react with hypochlorite and form monochloroamine, and monochloroamine further reacts with phenol and produce this indifferent blue. So when we check that pH of the solution, we found that below this acid, I mean less than 8 pH 8 or acidic pH. So this color, actually the color of indifferent blue is like this, but it is not forming. So why it is not forming? Because if you see this, I mean this monochloroamine is not forming, or it's unstable in this acidic pH region. That means we cannot do this color development method in this acidic pH. And also pH more than 11, we found some other problems. There are three problems associated with this. The first one is it cannot again this is not stable even if this monochloroamine form, so it cannot react with phenol. Even if it is formed, the color is not stable, it is converted to green for some other reason because of this. So we come to the conclusion that if you are working on this field and want to adopt indifferent blue method, you have to work on this pH 8 to 11. This is the optimum pH region we choose. So this is one problem. Another problem is that order of mixing, time of incubation, uh, dilution effect, and environmental temperature. So we work on all other we actually we have optimized all this method, and we found that time of incubation can be done 2 or more than 2 hours. There is no role for order of mixing. Temperature the below up to 40 degrees is fine. But one important point is that whether you have to incubate it in presence of light or dark. So till now, whatever the literature is reported, they have mentioned blindly that you have to incubate in dark condition. But there are no explanation given till now. Almost you can say 100% literature mentioned that you have to incubate in dark condition. But what we found that there is no role of light uh, on the indophenol blue compound. Although in presence of light there are some peak appears here, but we are only monitoring the peak which is at 630 nanometer, and you can see in presence of light also no absorptions decrease in here. So this peak is appearing because of this phenomena we have explained, but nothing to do with this peak. That means you can incubate it light or dark, it doesn't matter, light doesn't have any impact on this. So we have now tried to develop some catalysts and working on electrolyte. As I mentioned, that solubility is one of the challenges to produce ammonia. So first we have work on the electrolyte. We chose sodium tetrafluoroborate as a electrolyte. Why? Because if you see in water, it produces H3O plus ion plus BF4 minus ion, and this ion BF4 minus this is a superacid, so it will dissociate as BF3 and HF, and BF3 we know as a Lewis acid. So what will happen when you purge nitrogen in the aqueous medium? So some of the worker molecule will be replaced by your nitrogen. That means there will be some adduct formation, which we proved through NMR spectra also. There are some positive shift of there are some shift of this adduct formation, and we found out that this is actually responsible for producing more ammonia, or you can say bringing more nitrogen into the solution. So we finally proposed this mechanism. So our catalyst was MnN4 doped nanocarbon, and BF3 was NaBF4 was taken as electrolyte. So what we found that BF3 has a dual role here. So it is not only acting as an electrolyte, it is acting as a co-catalyst. How? This is the model, this is our catalyst MnN4. So BF3 attached to the catalyst from downside, and it has some impact to reorient the deband center of manganese. Not only that, when nitrogen absorb, so BF3 nitrogen, this adduct absorb on the catalyst surface. So because of this push-pull interaction, so nitrogen not only activated faster, so faster protonation also happened faster. If you see this reaction step, we have calculated all this reaction step with the help of our collaborator Dr. Ranjit Thapa. So Ranjit, what he did that we took 4 model. In one model we have nitrogen absorbed on the catalyst surface, another VF3 nitrogen, this adduct absorb on the catalyst surface. The third one is nitrogen from top side, VF3 from bottom side, and the fourth one is BF3 nitrogen adduct from top side and BF3 from bottom side. So for this all 4 model we took, and we calculated a del G for the nitrogen activation as well as fast protonation, and we found that this model, when BF3 is from the bottom side and BF3 nitrogen from the upside, it is actually the active catalyst, you can say, because you see the fast protonation del G is lowest in this case. So we came to the conclusion that BF3, as we thought, acting as a co-catalyst and helping nitrogen to activate and photonate. So this is the result. This is our electrolyte NaBF4, and we compared it with other electrolyte which is there in the literature, like HCl, NO2SO4, LiClO4 and KOE, and we found that as we expected, this is giving the better response. But the yield we found here is the production rate and yield is very high, although the fatigue efficiency is little bit less. So to address this, we change our catalyst here. So we choose different catalysts like oxygen functionalized boron carbonitride. So here the boron carbonitride was well known to activate nitrogen, but we functionalize this with oxygen because of this reason. When we have this oxygen, we saw that it is forming 5-member ring, and because of the highest electron density, it can push this electron density to the boron side, which is further pulled by the nitrogen, and because of this nitrogen-nitrogen bond can be elongated. So we have also calculated nitrogen-nitrogen bond for this defined compound. So this one is boron nitride, this one is for boron carbon nitride, and this one is for oxygen to boron carbon nitride. When you see this nitrogen-nitrogen bond, you can see here it was 1.11 Armstrong and it gradually increases, and the highest in this case. That means this nitrogen-nitrogen bond elongation is more here. That means oxygen has some role. What we thought that this push-pull interaction is happening, and because of the nitrogen activation is more. As we expected that Faraday efficiency increases from 18% to 34.7% in this case. So we developed several other catalysts. Because of time restriction, I am not going to the details. So I'll show you one more things here. So we have developed some catalyst here. This is called gold SNH2 metal semiconductor interface. So here we have shown that this interface playing some role for this nitrogen reduction. So here if you see this, their interfacial band structure. So when SNH2 form interface with gold, because of this band bending, the charge accumulation is happening. Not only that, this position of D band center is shifting, work function is decreasing, and conductivity is increasing. Because of all these factors, so it is helping for this nitrogen reduction. So I have discussed that in the introduction slide that HER is the competitive reaction for NRR. So if you want to increase the Faraday efficiency, so one way is that you have to reduce the HER. So here we what we have done that we choose the catalyst in such a way that SNH2 is the catalyst here. So we did this DFT study, and through DFT study we found that hydrogen absorb on the sulfur side. Okay. So hydrogen absorb on the sulfur side. That means our tin side is vacant, and which is actually acting as a nitrogen absorption. So in that way we can eliminate HER and can enhance nitrogen reduction reaction. And as expected, we found that Faraday efficiency is 49.37%. So which is almost close to the industrial level. So up to this all are the catalyst development. So by catalyst development we can reach the Faraday efficiency almost close to 50%. But as I have told you that this sluggish OER reaction is also one of the drawback for this NRR. So we try to improve this issue here. So this is the cell where we have cathode and anode. So as I told you, NRR is cathodic reaction, but in the anode, so OER means oxygen evaluation reaction is happening. But till now, most of the researchers are using platinum as a electrode here for OER. But we know that ReO2 is a very good catalyst for oxygen evolution reaction. So what we did here is we just compare with one side platinum and ReO2. As ReO2 is very good catalyst for OER, so whether it has impact on NRR or not, so we have checked this. So this is the reduction cyclic voltammetry diagram. So when we have FePC, so FePC means iron phthalocyanine as a catalyst, and we just catalyst is the same in both the cases. So what we did, we just changed this anodic electrode. So one case platinum, another case ReO2. So what we have seen when we took ReO2 as a counter electrode, so if you see this, the over potential for NRR is decreased. So here is the OER evolution test, OER test. So we changed the loading of ReO2, and we have seen this is the optimized loading. So when you have 4 mg per centimeter square loading of ReO2, so we have very less over potential of OER. So and with by adopting this method, what we have observed, the Faraday efficiency is going up to 67%. So although our catalyst is same, everything is same, electrolyte is same, but only by changing the electrode which is responsible for OER, I mean we are just improving the kinetics of OER. With this we can improving the kinetics of NRR also. So here we have calculated the full cell potential, Gibbs free energy, and equilibrium constant. And in all these cases, if you see this full cell potential is this is the thermodynamic value, and with ReO2 we have reached all this value is very close to this theoretical value. Not only that, we have calculated this energy efficiency. So energy efficiency, if you see when we took ReO2, this energy efficiency is 46%. When it was platinum, it is 20%. So this is the summary. With this, I want to thank all my students, funding agency, my collaborator, and thank you all of you for your kind attention.
Thank you.
If I take your technique of electrochemistry to produce ammonia, a typical plant in India produces 1,000 tons per day or 1,500 tons per day production, right? So if I take your cells, put it into a facility, how much land will I take? Because the first speaker said that the land is prime, so you can't have a facility which takes a lot of space in comparison to the current facility. So that's my first question. The second question is on the code that you mentioned, that you want to use ammonia as a hydrogen storage thing, correct? I want to ask, since ammonia is highly stable, so how are you going to get back that hydrogen from ammonia to use into, let's say, powering your cars or something else?
Yeah.
So
the first question what we ask is the value, I mean production rate and all other things. So here we have shown different work. So in some cases we have developed catalyst, in other cases we have worked on electrolyte, and we have also worked on counter electrode. So I haven't shown till now any single work where you have everything in good range. So industrial scale is totally different from the research scales. All data what I have shown in research scale. So now we have to go to this industrial. We are actually working on that. So I cannot comment on that value at the moment, and I cannot compare with the industry at the moment. So this is on research scale only. And the second question, what you have, what are the second
Ask the
question?
hydrogen.
Hydrogen. So there is a method actually. I mean, how will break ammonia to produce nitrogen and hydrogen. So this is not the challenge basically. This is I mean, method is there. How to break it. There are several methods by heat or electrochemical also. Even you can now people are working on to break it electrochemically also.
okay, thank you.
Okay, thank you. Thank you so much for very exciting talk.